If you're a resident of the tropics or live anywhere between 30 degrees south and 30 degrees north, you must have wondered why your weather forecasts aren't more accurate. That's because the tropics weather systems, the factors that create daily temperature and humidity, are decidedly different than they are in the middle latitudes. It's almost like we live in two different worlds, even though we're on the same planet. According to Dr. Ángel F. Corraliza, our guest on today's episode of the Boring Climate Podcast. Our guest is a Puerto Rican scientist and one of 22 recipients of the 2025 MacArthur Fellowship, also known as the Genius Grant. He studies tropical atmospheric systems with a focus on how water vapor and humidity play a key role in shaping the weather in this region. His work assumes significance given how most weather forecasting models are generally based on data from countries in the northern hemisphere, where weather and climate are different than they are near the equator. For lower income countries, models that understand weather systems unique to that region can improve forecasting accuracy and help with storm readiness, flooding preparedness, and more extreme weather adaptation and readiness. Hi, Dr. Aramis Corraliza. Welcome to the Boring Climate Podcast.
Hello, it is a pleasure to be here with you.
So we'll, kind of start off with some basics before we get into your work. You grew up in rural Puerto Rico and where you experienced tropical thunderstorms firsthand. Do you kind of recall when you realized that you wanted to understand this phenomena scientifically?
Yeah, so I was always interested in Earth and just weather and climate. When I was a kid, I'd be outside, just running around in my parents' backyard and on school, and I always kind of like stared at the clouds in the sky. Always thought that it was interesting to look at how the weather changed throughout the day. In Puerto Rico, we usually, the mornings usually be really sunny, and then as you move into the afternoon, you start seeing more clouds developed, and then will turn into like a downpour in the afternoon. So I always thought it was really interesting, but my interest didn't really fully flesh out until we got hit by Hurricane George in 1998. So when we had that and we were impacted by that, I thought the damage was so severe that like I just thought I needed to understand more of weather and what were the forces that would create something so destructive.
Right. And in kind of preparing for this episode, one of the things that I came across that you've often been quoted as saying is how the mid latitudes and the tropics are kind of two different worlds on the same planet. For the non academic listener, could you kind of break down what is fundamentally different about weather near the equator?
Yeah, so it's like I said, right? Like it's almost like we live on two different worlds in the same planet, right? And when I give lectures or I give talks to people, I usually show them an animation of weather patterns around our planet, right? So we have these satellites out in space, they're looking at Earth, and the geostationary ones are actually always seeing the entire planet. And so you can really see the differences between those mid latitude weather patterns and those in the tropical latitudes. So you see these whirling eddy like um, vortices that are in the mid latitudes. They're associated with warm fronts, cold fronts, and all the weather that's in between them. And usually these systems form as part of the jet stream. The jet stream has this massive wind pattern in the mid latitudes, very, very strong winds, like 10 kilometers above the surface. And this jet is unstable. And the jet creates the storm systems that you see moving from west to east, and that's a result of the temperature contrast that you have north of the jet in the northern latitudes. That's usually colder than south of the jet. Equator would, if you want to give a little bit of more generality. Uh, and this temperature contrast drives a lot of the weather patterns that you see in the middle latitudes. You see these cold fronts bringing in cold air, warm fronts bringing in warmer air, and so forth. However, in the tropics, you don't really see a substantial temperature contrast. Sure, there are areas on the surface, you get day and night cycles and so forth. But if you go at a higher elevation, you'll see very, very little changes in temperature anywhere in the tropics. So temperature doesn't really drive weather patterns to the same degree that you see in the middle latitudes. They still do play a role, but they're not as big as in the middle latitudes. And so what drives weather patterns in the tropics is what my research has been highly focusing on. And one of the key players in the tropics are these variations in water vapor and humidity. And so it is these large movements of water vapor masses that you see in the tropical latitudes that you see associated with weather patterns.
Right, which kind of brings me to my next question, which is that traditional kind of atmospheric science focused on temperature and pressure. And your breakthrough was recognizing that moisture or water vapor was actually a key player in tropical weather. How did you arrive at this, and why is moisture a key player?
Right. So for many decades, as people got interested in tropical weather and climate, or at least people from the northern latitudes became more interested in tropical weather and climate. People that lived in the tropics have always been interested in this, and as it became more global, the interest became more and more global. People started applying ideas from mid latitudes thinking and usually thinking about pressure, temperature, and wind patterns, and they were finding that it wasn't quite fitting in with the observations. There were some important discrepancies and things that weren't quite agreeing with observations. And so at some point in the 80s and the 90s, people started thinking this, what was missing in our theory? What's going on that we are not being able to explain in the tropics? And so the idea of moisture, especially moisture above the surface, we people knew the moisture near the surface was pretty important for instability, and humid hot days tended to be more unstable and could have more thunderstorms. But there wasn't as much recognition for water vapor above the surface, like at several kilometers of elevation, for example. And so this idea started taking traction, and new theories emerged in the 90s, for example, in the early 2000s, where water vapor played a central role in the dynamics of tropical weather systems. How is water vapor important is the key question here, right? And so the big insight is that tropical clouds, they're like plumes, or some of them are like plumes. And so you have this big puff of cloud going up, and the cloud actually interacts with the environment while it goes up. So while it goes up in the atmosphere, it entrains, and what I mean with entrain is that it mixes air from the surrounding environment into the cloud. So a cloud is just a giant packet of water, liquid water, right, in little droplets. So it's just tiny little droplets. So like rain, but really, really, really tiny. And the air that mixes into the environment, if that air is really dry, it'll evaporate those cloud droplets and it'll cause the cloud to fizzle out. But if the environment is really humid, the cloud can continue to develop and then organize into thunderstorms and rain and so forth. So people started recognizing that this how dry the what we call the free troposphere, so the air above the surface, was really really important. And so then that's coupling between the clouds and the humidity became the center point of new theories. And then as a student, I what I did was like I took this idea and kind of fleshed out a lot of the details on how these interactions happen in a relatively simple framework. So I didn't quite develop the idea, but I would maybe say that I helped popularize it, and by making it simple and digestible for broad audiences, so people can like look at these ideas and be like, okay, so this is how these interactions work and this is how they drive weather patterns.
Right. And do you think it's possible to kind of illustrate this by talking to us about how water vapor could probably cause a massive thunderstorm, say, in the tropics?
Right. So say that you have so let's talk about like what like I mentioned earlier, the dry atmosphere, right? So clouds like to form, right? If you are over the ocean, you're just constantly evaporating.
Mm.
So you're humidifying the atmosphere just by the fact that you're over the ocean, right? So you have all this water. A lot of this water starts evaporating, so the atmosphere starts to get more humid. However, if the atmosphere above the ocean surface is really dry, you can form clouds, but the clouds will mix with this dry environment and they'll tend to fizzle out. So you don't really get this thunderstorm development that you're thinking would happen. But if your environment is humid, a cloud goes up, it mixes with the environment, but the environment is pretty humid, so the cloud doesn't fizzle out as much as it if it's dry, right? So the important thing here is that in the tropics, if it's humid, you actually do have enough energy in the atmosphere for that cloud to continue going up really, really high. And so the more humidity you have, the more of these clouds can just develop and continue growing. And so at some point, you just get enough of them that are growing that they become thunderstorms, right? Like, so these clouds can just keep growing and growing and growing. And in really humid environments, they can just collect, get together, and form a big thunderstorm, and that leads to rain. So the big key thing here is that you need an environment that's sufficiently humid to support not just one cloud that can develop into a thunderstorm, but like numerous of them, right? So like a large quantity of them, so they can like in aggregate become a larger scale system that creates heavy rainfall. So this is what we see, for example, in like the monsoons and the intertropical convergence zone and in many of the weather systems that we study in my research group.
Right. And another core research area of yours is something many people may never have heard of, which is the Madden-Julian oscillation. What is this kind of massive atmospheric phenomenon, and why should people care about it more importantly?
Right. So the Madden-Julian oscillation is actually one of the most important weather phenomena in the tropics that, and probably the most important one that people don't know about. So generally, people know about El Nino. That I think is like a pretty well-known tropical phenomenon. The Madden-Julian oscillation, or MJO for short, is about as important as El Nino is, but a lot less known. And so, what is DMJ? What is this thing that we're talking about? So, if you look at images of clouds in the tropics, you might occasionally notice that there is a very, very large cluster of clouds that forms, especially over the equatorial Indian Ocean, and it moves eastward very, very, very slowly, like about 5 meters per second. So we're talking about something that doesn't move very quickly, but it is very, very large. So how big is this large cluster of clouds? We're talking about like a bunch of thunderstorms, like a ton of them, all like organized together in this big, big beast of a weather system. So we're talking about something that we call planetary scale. So it's about comparable to this to the size of the planet. So size, or at least the circumference of the planet. So we're talking of something that is at least 10,000 kilometers large, or even larger than that. And to give a little bit of reference, that's about the size of Russia. So Russia is the biggest country on Earth. Russia could fit inside the MJO. That's how big the MJO is. Uh, in association with all these thunderstorms that you see, you have wind patterns, and you have big modulation of weather patterns, and as the MGO traverses. So you're talking about changes in tropical cyclone activity, rainfall, overall weather conditions. So overcast skies, humidity, temperature, not so much, a little bit temperature, but not too much. And because of how big the system is, this is about the size of El Nino as well. You also have big impacts around the world, not just in the equatorial latitudes, but also at higher latitudes as well, including atmospheric rivers and temperatures and so forth.
Right. And with respect to the impact of climate change, the MGO is set to influence everything from tropical cyclones and how they form to monsoon intensity and therefore floods. And you've also, in some places and in some of your research, called it potentially the next El Nino. In terms of forecast importance. So, if we could kind of predict the MJO a few weeks out, what becomes possible?
So yeah, so the MJO is part of what we call the seasonal to subseasonal prediction, and it's
Okay.
part of that prediction gap. So we are actually at this point we can predict weather up to like a week, reasonably well, with some exceptions. But we have a decent amount of weather prediction capabilities at the weekly time scale. And of course, at the seasonal and longer time scales, we also have decent prediction because seasons do play out in a very predictable way. And you also have patterns like El Nino, which we haven't really fully understood how to predict that well, but we've made a lot of advances in predicting El Nino, especially as it gets closer to December. That's usually when El Nino is strongest, and our ability to predict El Nino gets better the closer we get to the holiday season in the northern hemisphere. So then we have this seasonal to subseasonal. So it's actually too long of a time scale to be weekly, so it's longer than a week, but too short to be seasonal. And so we tend to have worse spreader predictions capability at that time scale that at the two other edges. And one of the reasons why we have this issue is because we don't really have really accurate predictions of the MJO. And so if we had that, we'd be able to, for example, say uh, with weeks in advance whether, for example, tropical cyclone activity will pick up in like 2 3 weeks, right? So we're not really saying whether it's going to rain or not, right? Because I think that
Hmm.
would still be very difficult 2 3 weeks in advance, but it can give you an idea of the variations that might be going on in a couple weeks. So whether we're expecting to see more tropical cyclone activity, or if we're expecting to see more likelihood of floodings in 2 or 3 weeks due to the existence of the MJO. So it can't give you the exact details, but it can give you an idea of how things are going to be different relative to this week, for example.
Right. And how does a warming planet, for instance, affect the MJO? So, what happens if we're adding more, greenhouse gases to the atmosphere? And what does all this mean for people who live in the tropics?
Oh, so climate change is going to change a lot of things. And unfortunately, even though we don't talk about it very much, I think the tropics are a lot more susceptible to climate change than the middle latitudes. Generally, the tropics are not going to warm as quickly as higher latitudes do. The amount of warming is actually smallest in the tropics compared to the middle and high latitudes. But that doesn't mean that the impacts in the tropics are not profound. So one of the things that we see in the tropics is that the amount of humidity and how
Hmm.
much it varies in the tropics is actually highest compared to any other latitude on Earth. So the highest amount of water vapor variations occur in the tropics, and that's because of an important physical constraint we know as the Clausius-Clapeyron equation. In digestible form, this equation tells us that the capability of the atmosphere to hold water vapor increases exponentially with temperature. So the warmer the atmosphere is, the higher the capacity of the atmosphere to hold water vapor. And because the tropics are the warmest latitudes on Earth, the tropics have the highest capacity of holding water vapor on Earth. And so that generally means that the capability of the tropics to create rainfall is much higher than the mid latitudes. So you can actually rain way harder in the tropics in theory, right? When it rains hard, it can rain really, really hard in the tropics, way more than any other latitude. And in the same way, you can actually have extreme dryness in the tropics in ways that you don't see in other latitudes. So you're also setting up the potential of like really intense droughts, for example. And if you think about heat waves as well, so heat waves in the tropics do happen, and they're quite deadly. Uh, and the reason why heat waves in the tropics happen, even though temperature doesn't vary very much, is because you can actually vary temperature a little bit, but you can also vary the humidity. And so you can actually have episodes in which your temperature is a little higher, but the humidity is a lot higher. So we call these things moist heat waves. And these are actually episodes where the humidity is very high and the temperature is high enough so that feels really, really uncomfortable for people. And so these are the three things that we're really concerned about with climate change. We're concerned for the capacity of the atmosphere to create floods to become sharper, so we can have more extreme floods. We can have more intense droughts because the evaporative capacity of the tropical land can increase. So you can actually evaporate more quickly because the atmosphere can hold more water vapor. So we'll just grab it more quickly in a warmer climate. So more droughts, and then deadlier, potentially more intense and deadlier heat waves. And so these are the three things that we're worried about. And the Madden-Julian oscillations, the MJO modulates all three things. And there's a fourth one, right? The fourth one that I completely forgot about, and that's because the oceans are warming and the atmospheric capacity for water vapor increases, then the potential intensity of tropical cyclones goes up as well. So we could potentially, when the atmospheric conditions are really favorable for a hurricane or a typhoon or a cyclone, they can get really, really strong, stronger than what we they can right now. So their impacts also become more severe. And so the Madden-Julian oscillation can influence all four of these factors. So we're talking about modulations and potentially more intense and deadlier extreme events in a warmer climate. The MJO itself is changing as the climate is changing. It is becoming stronger and faster and more regular. So in their current climate, the MJO can exist. It can have you can have two or three events and then it stops and then there are no MJO for months and then it kind of comes back. But in a warmer climate, our climate models are suggesting that it'll kind of be active more continuously. So you will have longer periods of activity with shorter breaks in between, and so you'll see more of the MJO's impact and modulation more frequently in a warmer climate. So the MJO's modulation of rainfall and all these things are also going to become more pronounced. And because it moves more quickly, it'll its recurrence will be faster. So instead of recurring every 2 months, it'll recur every 45 days or so. So we are talking about important and pronounced impacts that can actually change the well-being and livelihood of people, right? So we're saying about things that can be predicted, right? So people might not notice it with good weather predictions, but when extremes happen, they can be more dangerous for people than what they are right now.
Right. And this is actually one of the things that your research is trying to, this is a gap that your research is trying to bridge in improving the way we are predicting for the tropics, considering all of these complex phenomena that add to the existing vulnerabilities in the tropics. What are these gaps that you have identified, and what is your research doing to kind of bridge it?
Right. So, like we were talking earlier, right? Like what I've done research wise have been really put front and center the importance of water vapor as a variable, right? Or as a
Right.
field that really modulates weather patterns in the tropics, or that drives patterns in the tropics, right? You have a lot of water vapor that tends to create favor cloud development. So you have more thunderstorms and more rain in these regions. And regions where the water vapor is low, then that suppresses cloud development and tends to suppress rain. And so what we've been identifying is, or trying to understand better, is how water vapor does this, right? Not just at the small scale, but at the large scale. And then how that translates into our weather patterns, right? And so weather patterns, right? The thing about weather patterns that maybe I didn't quite mention and want to clarify for the audience is that weather can be thought as chaotic. Maybe people think that it's kind of random and stuff, but weather systems are actually not random. They actually are predictable. And even though they are chaotic, and when I mean about chaotic is that they're actually difficult to predict. They're difficult to predict, but not impossible. That's kind of the definition of chaotic here. And so when a system is chaotic but predictable, that means that we can actually improve our ability to predict them. And so what we've shown in our research is that, first of all, that the tropics is incredibly rich in the types of weather patterns that it has. It's actually richer than the mid latitudes in terms of the types of weather patterns that it has. So, and that's interesting in that you have a lot of types of weather patterns, but it actually poses a challenge in that we actually need to understand all of them pretty well in order to predict weather in the tropics really well. And so what we've been focusing on is on the weather patterns that are actually evolved slowly. So it turns out that through the theory that we developed, that these slowly evolving weather patterns are the ones in which water vapor is really important. So the faster ones are, it's not that water vapor doesn't matter, but it's not as important as the slow ones. The slow ones is where the water vapor is really, really important. So we've been characterizing how these weather systems evolves and what are the processes that water vapor, in which water vapor modulates rainfall. And so we found that actually is this horizontal transport of water vapor, so moving from the humid areas to the dry areas or vice versa, that actually creates a lot of richness in water vapor. And we've also characterized then how then this water vapor impacts the clouds. And so what we found is that a lot of weather patterns, even though they're different, easterly waves, tropical depression waves, monsoon low pressure systems, the MJO. They're very, very different weather patterns, but they share similar processes in their evolution. So it actually simplifies things from a weather prediction standpoint, because instead of understanding all of them separately, you can actually collectively collect them all together as a type of weather phenomenon. And that if we understand the processes of this type of weather phenomena, we can understand all of these weather phenomena together. And so it turns out that the challenge with weather and climate models is that they're actually not that sensitive to water vapor, especially above the surface. So they don't get these weather patterns super well, but we know why. And so there has been a lot of advances in simulating and these weather patterns. So our ability to predict tropical weather patterns is going up. It is still not satisfactory. I think it is not where it should be, but I think with the help of my group and many many other scientists, right, that are working on this, I think we are identifying a lot of simple and straightforward ways in which we can understand these processes and then translate them into weather prediction or climate prediction, right?
Right. Right. Which kind of brings me to my next question. If very briefly and very simply, you could tell our audience how exactly you do the modeling. And I'm sure it's extremely complex and hard to break down in a podcast, but so that anyone interested in kind of taking up this might get a kind of primer on how you do what you do.
Well, actually, so a lot of the modeling that I do is theoretical.
Hmm.
So we do. I personally, well, I do. And along with my group, we do pencil and paper, or nowadays it's like iPad and and a stylus, or like whatever tablet you use, right? Like so nowadays a lot of my theory on a tablet, and so what we do is that we take the equations of motion. So for people that are not familiar, that haven't taken weather and climate or oceanography, for that matter, the atmosphere and the ocean move on the basis of a system of equations that we know as the primitive equations. So the primitive equations are actually very very complicated. So you have three equations of motion for east west north south up down. We have an equation for the thermodynamic equation, so the first law of thermodynamics. We have what we call the equation of state, which just describes the state of the matter. So we have an equation for liquid, an equation for gas, and then we have an equation for water vapor and its transformations, and then a bunch of other equations. So we're talking about like at least six or seven equations, potentially more, depending on uh, how uh, how um, how much detail you want in your model. So we take all these equations. These are the equations that go into climate models and weather models and ocean models. And so what I do is that I simplify these equations. So I want to extract the important information to understand certain phenomena in the most simple framework as possible. So what I do is that I take all this math and just knock out a bunch of equations and just bring it down to just one or two equations that describe a system very simplistically. So we call this a theoretical model, right? It's still a model. You can actually just write the equations that you get on your laptop and then run whatever code you want and get a very simple description. And so what's important about this is that these models don't predict weather themselves, right? They're too simple to make weather predictions, but they are helpful in giving us guidance, right? They help guide us in helping us to understand what are like the really basic principles that guide certain weather systems. And if these simple principles are not in our forecasting models, then we can't really hope to get these systems well, right? So it really is more of like a model that helps us understand conceptually how systems work in a really idealized setting, so we can go back and understand better our climate models or even help improve them.
Right. And one of the kind of underlying themes of your research is accurate data generation for localized weather forecasting, specifically in the tropics, most of which is in the developing world, right? And for this, what is your view on the role that citizen science might be able to play in collecting this kind of data and helping scientists such as yourselves understand this better?
So I think it's important for people to know that the tropics is the most data. It's one of the most data sparse regions on Earth. So if you look at where observations are being made, observations are largely being made in the mid latitude continental regions. So the United States, Europe, China, for example, they're making a lot of observations. And so if you compare to the tropics, there's a lot less observations, and a lot of countries are increasing the amount of observations that they're making. India, for example, there's a lot of development. Southeast Asia as well, but a lot of the tropics is also ocean. So it's not an area that's easily accessible for observations either. And so we rely a lot on satellites to make observations of the ocean. But if people are doing observations, for example, citizens that are like out and ship commercial ships, that's oceanic observations that we don't have, right? And they're important in that they people sharing that and making things available for us. It does help us actually understand and have data that we otherwise wouldn't have, right? So that's one of the key things, right? But I'm never gonna like go be against people like using observations to learn themselves, right? Like I think citizen science as an educational tool is also really important, right? Because you can actually get people to make observations, and you can actually get them to like look and see how humidity and temperature are changing on a daily basis, and then you can go to like a high school or like a company and then be like, look at the data that you collected, and separate this by the monsoon season or the dry season, and see how the stuff that you've observed yourself is actually showing you the patterns and the weather systems that are evolving in your region. So it's two things, right? Like it's useful as a research tool in helping us understand because the data in the tropics is generally sparse, but it's also an important educational tool for people so that people themselves can actually firsthand learn and understand the weather patterns that are driving, weather and climate where they live.
Right. And to kind of this end, you also host a Spanish language podcast yourself. And I think the idea behind that is to make atmospheric science a little more accessible. In your view, why is science communication, specifically in Spanish, important to you? And what role do you see, scientists playing in public discourse about climate?
Yeah, so this is a great question. And so the reason why I started the podcast was it was two things, right? Like generally there's been a lot of people doing science communication, and science communication really has taken off in the last decade or so. And you see a lot of YouTube channels, TikToks, Instagrams, people generally talking about science, very, very enthusiastic about what we've been learning. But in Spanish, there hasn't been a lot. The amount of resources and educational tools for people that predominantly speak Spanish is not at the same level as English. So that's one thing. And then the second thing is that we do, even with the rise of communication, right? We do have an issue in that like anybody can create content, right? And so and this is great and bad at the same time, right? It's great because there's never been as much content as there is right now. There's so much to digest. But also it's bad in the sense that anybody can make content, and not necessarily everybody that makes content knows what they're talking about or is giving the appropriate, science, or the most recent science or accurate science to the public. And so I thought, and I talked to my colleagues, is like we really need to make something that is not just accessible because people want to learn, but also accurate, from the experts, And I talked to my friends and colleagues. I had some friends from Puerto Rico back then who were saying it's like, oh, there's a lot of junk out there. You have a PhD, you're gonna be faculty, you're gonna be a professor. People are gonna trust you, in what you say. And so this kind of led to this long journey of like creating the podcast, but also creating social media channels where I discuss science content in a generally accessible manner, but in a way that digests it. So it's just two things, right? Like I think there is a need. I think the content creation has never been easier, right? And people want to learn. I've learned from interacting with people that people are generally curious and want to learn, and so I that content should be there. If people want to learn, they can access it. But it also needs to be accurate content that is coming from the sources and the people that know how to like communicate it. And like what better way than the scientists themselves coming in, right, and showing people like what we've learned in, and I think it's super important to do that, because like what's the point of me keeping the knowledge to myself, right? Like I think the key thing is to people to learn all my knowledge, right? Like I don't think it's as valuable for me to keep that knowledge for myself. I think it's a lot more valuable when that is shared with people. And it adds a third element here that I think um, we don't often talk about it, and that is that people don't most people don't know scientists, right? Like like there are not that many scientists in the world, and so I think there's generally this stereotype of who we are, that we're these people that like to be left alone and whatnot. And not necessarily like the most collegial or nicest people on earth, and there are people like that. That's for true. But like many scientists, like most scientists, we're just people, right? We're not that different from most people. We have our own lives, we have personal lives, we have families, we have things that we strive for outside of our jobs. And I think it's important for people to see that too, that we are a lot more relatable than what people think. We're just people too, right? That, and seeing that relatable aspect of ourselves is part of why I also do science communication.
Right, and I think that's truly a very critical part of your work. Even though a lot of your work is so technical and so generally hard to access, the fact that you take time off to break this down, I think that's incredible. So thank you so much for taking the time to be on our podcast and for sharing your insights with us.
Oh, it was a great pleasure. Happy to discuss. If you have any other questions in the future, just feel free to reach out. I'm happy to just continue this conversation, and continue, like the due diligence that we're doing for people, right? Like talking about science and talking about what we've learned, and the impactful research and communication that we're doing.
Super, thank you so much.
Thank you.